Hi everyone. Today we are discussing about radical chemistry. In this topic, we will discuss about key points of radical and strategies and problem solving approach. So first is key points. I have listed out some key points. These are the 13 key points. In this, first one is tributyl radical. This will work as a halogen obstructor in any reaction. Okay. If AIBN is given, so it will undergo homolytic cleavage in the presence of heat and sunlight to generate another radical by hydrogen obstruction. In the presence of mercury acetate, it will work as addition or alkene compound. So NaBH3 will abstract HgOAsC compound to create an alkyl radical, while samarium iodide is work as on addition on ketone and create an ketyl radical anion, while manganese triacetate abstract alpha hydrogen from ketone compound to formation of alpha keto radical. While Me3 SN Me3 is an symmetrical compound, so it will undergo homolytic cleavage of SN bond and then abstract hydrogen atom. While RCOO-COR is an also a symmetrical compound, it will undergo homolytic cleavage of oxygen-oxygen bond, so then abstract hydrogen atom. So these are the two symmetrical compound, and this one AIBN is also a symmetrical compound, so this will undergo homolytic cleavage. While tributyl tin chloride and NaBH3CN act as to minimize the amount of tin hydride, while ROCl, RONO and ClNO, these three reagents undergo homolytic cleavage because of weak bond of OCl, ON and ClN bond. The last one is protonated N-halamine is an example or reagent of Hofmann-Leffler-Freytag reaction. So let's look to our strategies. We know that in the radical reaction, the source of radical is light or heat. Okay, so first we have to identify that in the radical reactions, radical initiator is given or not. If radical initiator is given, so this radical initiator generate another radical. So this radical have two possibility. One is halogen obstruction, another one is addition to a pi bond. So let's consider if compound this radical obstruct halogen atom. So next step is we have to check resonance is there or no. If resonance is there, so next step is hydrogen obstruction. So this after resonance, that radical compound will obstruct hydrogen atom to stabilize or neutral. If resonance is not there, so there is a direct conversion from halogen to hydrogen obstruction. This radical undergo addition to a pi bond. So next step we have to identify that resonance is there or no. If in compound resonance is there, so we have to identify leaving group possibility. If leaving group possibility is also there, so we have to check again. After that leaving group, some radical will form. So this radical again will undergo addition to a pi bond or no. If there is a possibility of addition to pi bond, so we have to repeat out these three steps. So this after repeating these three steps, after that the new radical will undergo hydrogen obstruction. If in the radical reactions, if radical initiator is not given, so we have to identify weak bond, because in the presence of heat or light, we can cleave weak bond homolytically. So weak bond homolytically, after that cleaving weak bond, so there are two possibilities that the radical will undergo delta hydrogen obstruction or allyl hydrogen obstruction. So if compound will undergo delta hydrogen obstruction, so formation of delta halo compound. So this delta halo compound have possibility to undergo nucleophilic substitution reaction. Similarly, in the allyl hydrogen obstruction, to form an allyl halo compound, so this allyl halo compound also undergo nucleophilic substitution reaction. So next one is problems. In these problems, we have to identify the first product. What is the name of the reaction? What are the key points? And what is the strategy we have applied? So here in the strategy, source of radical is given and weak bond is also there, and there is no radical initiator. So in the presence of heat and light, this weak bond and wear bond will cleave homolytically. This is the strategy. And key point is here, in the presence of acid, this will form protonated and bromoamine compound. Okay, this one. And after that, this protonated and bromamine will treated at 140 degrees Celsius to undergo Hofmann-Leffler Freytag reaction, and that is our product. If you want to see the mechanism of the Hofmann-Leffler Freytag reaction, you have to follow our previous videos. So in the next one reaction, this cyclic amide compound, this nitrogen will act as a nucleophile at I2 to form a protonated anidoamine compound. This protonated anidoamine, so this protonated anidoamine in the presence of light will cleave homolytically to form this compound and undergo Hofmann-Leffler Freytag reaction. Both are the same reactions, Hofmann-Leffler Freytag reactions. So in the problem third, source of radical is given and weak bond is also given. These are the two strategies, and key point here is this ON bond is weak bond. This will cleave homolytically. This oxygen radical will obstruct this delta protons. So why this delta protons? Because of this proton is near to this oxygen radical. So this will obstruct this delta proton. After that, this delta radical and this N radical will couple here to form this compound. This is a Barton type reaction. In this, there are two states given. One is the source of radical, another one weak bond. This is the OCl. This is also a key point, OCl bond. Okay, so in the presence of light, this bond will give homolytically. This oxygen radical will obstruct the delta proton, alpha, beta, gamma, delta, this delta proton. And after that, this delta radical will couple this Cl radical, and this oxygen OH will act as a nucleophilic substitution to form a tetrahydrofuran. This is also a Barton type reaction. In the next one reaction, N-chlorosuccinamide in presence of HNO. There is one strategy is given, that is light. Okay, in the presence of light, key point here is NCl bond. This is N-chlorosuccinamide. NCl bond will cleave homolytically. So this nitrogen radical will obstruct this CH2 radical. Where CH2 radical, we can write Bn benzyl group as a CH2PH. So these CH2 protons are allylic protons. So this nitrogen radical will obstruct this allylic protons to form a allyl radical. Okay, this allyl radical and this chlorine radical will couple here, and this oxygen act as a nucleophile to form a cyclic compound. This is a type of allylic bromination reaction. Similarly, in this reaction, here coupling of this carbon and this carbon will take place and leave out as a SN-butyl-3 and bromide, tributyl tin bromide compound in the presence of AIBN. So this is also a type of halogen abstraction reaction. This is not a name of the reaction. In this reaction, this is the source of radical initiator. This AIBN obstruct this proton, this tributyl tin radical obstruct this halogen. After that, this alkyl radical will form. This radical undergo resonance to form a new compound. This is type of halogen abstraction. This is also a not name reaction. This is also a selective reaction. Here strategy given is a HNO, that is the source of radical, and key point here is weak bond. Weak bond is here N-bromide, nitrogen and bromide compound. So NBS is a N-bromosuccinamide. So in this NBr bond will return. So this NBr bond will cleave homolytically, and after that nitrogen radical will obstruct this hydrogen. Why this hydrogen? Why not this hydrogen? Because this hydrogen and this hydrogen both are what? Allylic hydrogens. So this allylic hydrogen is secondary while this is primary. This secondary hydrogen is near to oxygen, but there is no electronegative element attached to near this. So this proton is highly acidic or highly reactive to react with nitrogen radical. After that, bromine radical will couple here to form a new bromo compound. This is also a allylic bromination type reaction. In this problem, the strategy given here is radical initiator. This radical and AIBN will obstruct this proton to create new tributyl tin radical. This is a difficult reaction to understand. We have to approach the strategy here. By approaching the strategy, we can find out the product easily. So let's look towards mechanism. In this tributyl tin radical will undergo addition to a pi bond. Why this is not undergo halogen obstruction? Because in this compound there is no halogen atom. So here one strategy given here is addition to a pi bond on this C double bond S atom. So after that this alkyl radical will form to cleave this oxygen bond. Okay, this alkyl radical undergo resonance or addition to a pi bond with this C double bond N to create this nitrogen radical. This nitrogen radical also undergo resonance to cleave this ring. Okay, after that this nitrogen will leave out as a N2 and this is a trans pH CH double bond CHPH. After that this radical will stay here, alkyl radical. This alkyl radical also undergo addition to a pi bond, then form this primary radical. This primary radical will obstruct the proton directly from butyl 3SNH to form a neutral compound. This is a Barton deoxygenation reaction. Here 3 times. First time addition to a pi bond of butyl 3SN radical to this C double bond S. After that addition to a pi bond of this radical to C double bond N. After that addition of this radical to this C double bond C. There are 3 type of addition of pi bond in this mechanism occurs. So that's why we have to identify what type of strategy we have to approach. For get latest information, you have to subscribe our channel, comment and like.